In this video, we're going to have a short discussion about the use of polar coordinates. Polar coordinates are used as an alternative to the standard Cartesian coordinates for describing points in the plane. In this course, we're going to use polar coordinates to describe certain regions so that we can compute the integrals, the double integrals over those regions in an easier fashion than we would if we were using the standard Cartesian coordinates. So to begin with, we'll actually start with a quick overview of how to define the polar coordinates of a point and look at how we can convert back and forth between the polar coordinates and the Cartesian coordinates. So let's say we have a point in the plane. And so here are the x and y axis. Here is my point that I want to consider. Ever since you learned how to graph things in the plane, you have learned how to find the Cartesian coordinates of a point. And so the way to find the Cartesian coordinates of a point is we start at the origin, we move along the x-axis until we're directly above or below that point. And then, once we're directly below or above it, we move vertically up or down until we hit that point. And these two line segments that we drew, we're going to say have length x and length y. And assuming these are both positive, this is the point x, y. Right, these are the Cartesian coordinates of this particular point. If the point were in one of the other quadrants, then one of the x's, x or y, or possibly both, would be negative, and that would just indicate that we're going in a different direction, and we would have the absolute value of x or the absolute value of y for the lengths of these segments. But in any case, every single point can be described as an ordered pair x, y in this way, and every ordered pair x, y describes a point in the plane. Right? So there's an alternative way that we can locate points in the plane, and that's using polar coordinates. So the idea is that we're going to start by looking at along the positive x-axis from the origin. We're going to rotate until we're looking directly at the point x, y, and then consider that distance from the origin to the point x, y. And so in polar coordinates, instead of caring about the distance, the horizontal and vertical distance to the point, we're going to consider the angle that we turn, which we'll call theta. So this is the angle from the positive x-axis to the point where you're staring directly at the point xy, or at the given point. And we also care about the distance the point is from the origin. And so we would describe in polar coordinates this point as r theta. Right? So a given point r theta is a point that's r units from the origin in the direction that makes an angle of theta with the positive x-axis. It should also be clear that every point has a set of polar coordinates. In fact, every point has infinitely many polar coordinates. Notice that for this particular example, it looks like theta might be pi over 3 or something similar. But we could also have theta being 7 pi over 3. That would have the same angle. It would go all the way around one full rotation, and then this little theta here. We could also describe it as negative 5 pi over 3. So we can change theta to be any coterminal angle with pi over 3. And we could also, we're not going to worry about this so much, but if r were negative, what that would mean is that the point is going to be in the opposite direction that you're looking. So if that happens to ever come up, that's what a negative value of r would mean. So these are two different ways to indicate points in the plane. And this picture here tells us everything we need to know about how to convert back and forth between the two coordinate systems. So using right triangle trigonometry, it's clear that the cosine of this angle, theta, it's the adjacent side over the hypotenuse, which is x over r. And the sine of theta is the opposite over hypotenuse, which is y over r. And if we take each of these equations and multiply them on both sides by r, we see that x is equal to r cosine theta, and y is equal to r sine theta. So if we need to convert from polar coordinates to Cartesian coordinates, these are our formulas. We can compute x and y as r times cosine theta and sine theta, respectively. To convert in the other direction, if we know x and y and want to find r and theta, which is actually for integration what we're going to want to do more often, we want to compare, we want to get r, we can use the Pythagorean theorem. Right? We see that r squared is equal to x squared plus y squared. This is just the Pythagorean theorem for this particular right triangle. And so if I know x and y, if I know the Cartesian coordinates, I can square each of them, add them together, and that is the square of the first polar coordinate. Likewise, if we want to get theta, x, and y involved, we see that tangent theta is equal to y over x. And so these are the ways to compute from xy to r theta. One of the benefits of polar coordinates is that certain types of graphs are quite easily drawn or described in polar coordinates that might be a little bit more difficult to describe in terms of Cartesian coordinates. So a couple of the common graphs, and these are going to be ones that we're going to care about a lot with integration. If we have a graph of the form r equals a constant a, right? So a here is a constant. Right? So if we think in polar coordinates, what does r equal a mean? Well, r is the distance from the origin. That was how the r coordinate was described. And so saying r is equal to a fixed number is saying I want all the points that are a fixed distance from the origin. And in geometry, we call that kind of a figure, a circle. So r equals a is simply a circle centered at the origin with radius a. Right? So as an example, r equals 1 is the unit circle. Right? So circles are much easier described in polar coordinates than they are in Cartesian coordinates. Cartesian coordinates, we'd have x squared plus y squared equals r squared. In this case, we just have r equals the radius of the circle. Of course, this is a circle centered at the origin, but it's not too terribly difficult to get one that's not centered at the origin either. But in this particular case, circular shapes are represented much easier with polar coordinates than they are with Cartesian coordinates. Another common graph comes from setting the other variable equal to a constant. So if theta is equaling a, right? So theta is in polar coordinates describes the angle made with the positive x-axis. So theta equals a wants to describe all the points that make an angle of a radians with the positive x-axis. Right? So this is a line through the origin. Making an angle of a radians with the positive x-axis. So for example, if I had theta equals pi over 2, this would be the y-axis. Right? Every point on the y-axis, in order to look at that point, we would have to start at the positive x-axis and rotate pi over 2 radians. And remember that we're allowing r to be a negative number to describe in the opposite direction. So even though when we rotate pi over 2 radians, we're only looking at the positive y-axis, we get every point on the negative y-axis by taking r to be a negative value. Another example of a line would be theta equals pi over 4. If we rotate pi over 4, we're looking at a pi over 4 radian angle or 45-degree angle. And the line that we get by looking forward and backwards at that angle is y equal to x. Right? So we can describe lines through the origin with also a single variable equaling a constant. So now that we know how to graph lines and circles in polar coordinates, we can use polar coordinates to describe all sorts of regions in the plane that would be difficult to describe with Cartesian coordinates. Right? So for example, let's consider this region here. Right? So over here, I'm going to have a ray that is part of the line theta equals pi over 6. Here I'm going to have a ray that's part of the line theta equals 2 pi over 3. And the region I want to describe is this region here. So it's the region in between these two circular arcs. And so all we really need to know is what these circles are. So this might be the circle r equals 3. And maybe this is the circle r equals 5. Right? So this is the region between the circles of radius 3 and 5, centered at the origin, and lying between the rays pi over 6 and 2 pi over 3 with the positive x-axis. And so this region, if we wanted to describe in terms of our Cartesian coordinates, we'd have to find the equations of these. We'd have to say x squared plus y squared is between 3 and 5, and we'd have to find some way to describe these angles in terms of x and y. So we'd have to find terminal points on there, and it's not the most pleasant thing to do. And then if we had to integrate over this region, it would be even more difficult. But in this case, we can simply describe this region in the following way. We can say that theta lies between pi over 6 and 2 pi over 3, and r lies between 3 and 5. And so we can describe circular-based regions like this pretty quickly, and it's also very simple. In the next video, we're going to look at integration over regions described by polar coordinates, and notice that in terms of the iterated integrals that we were talking about in the previous video, this sets up nicely because all of these boundaries for the inequalities, all the endpoints here, are constants. And even if theta, or even if r has to range between two functions of theta, we always have theta between two constant values. We always have the starting angle and the ending angle to consider. And so this lines up really nicely with being able to compute an iterated integral to describe the double integral over a region. Just like Cartesian equations, sometimes polar equations do take a little bit of effort to graph. So for example, let's say I wanted to graph r equals 1 minus cosine theta. All right, so this equation involves both variables r and theta, so it's not going to fall into either of the categories that we just saw. It's not going to be a line, it's not going to be a circle, it's going to be something else. And so whenever we have a graph or an equation, we want to find a graph, we don't know how to graph it, we can always make a table of values and plot them in the plane and kind of connect the curves in sort of a nice, logical, smooth way. And so in this case, we're going to make a small table with values of theta and r. And I'm going to pick values of theta that are easily computed. So I'm going to use 0, pi over 2, pi, 3 pi over 2, and 2 pi. If you want to get more refined and compute pi over 4s, or pi over 3s, or pi over 6s, you can do that. You can do as much as you need to in order to get an idea of what this shape looks like. And for each of these values of theta, I'm going to take their cosine value and then subtract that value from 1, and that will produce r. So for theta equals 0, I get 1 minus the cosine of 0, which is 1 minus 1, which is 0. Okay. Cosine of pi over 2 is 0, so r is 1 minus 0, or 1. Cosine of pi is negative 1, so r is 1 minus negative 1, or 2. Cosine of 3 pi over 2 is 0, so 1 minus cosine of pi over 2 is 1 minus 0, which is 1. And cosine of 2 pi, like cosine of 0, is 1, and r is 1 minus 1, which is 0. Right, and so here are 5 values that we can use to plot our graph. So I'm going to label 2 units in each direction. Notice that our R value, the largest that we have there, is 2. And so that is, at least in the points that we're going to draw, the furthest we're going to get from the origin. All right, and so we're just going to plot each of these points one by one. So for the first point, 0, 0, we're going to turn 0 radians, which means we're going to look along the positive x-axis. We're going to go out 0 units and mark our point, and of course that describes our origin. Right? So this point here is corresponding to theta equals 0, that point in our table. When we go to pi over 2, we're going to be looking up the positive y-axis, and the r value here is 1, which means this point is 1 unit along that line. Right? So we have this point up here. So this is corresponding to theta equals pi over 2. The third point, theta is pi, so we're going to look along the negative x-axis, and we're going to go out 2 units. That's our r value, so we're out here. Okay. So this is going to be theta equals pi. The fourth point, 3 pi over 2, we're looking down, an angle of 3 pi over 2 radians, and we're going out 1 unit. So this is with theta equals 3 pi over 2. And the last point, the fifth point here, is we face 2 pi radians, which is we make a complete rotation and continue facing in the positive x direction and go out 1 unit. And when we do that, we see that we get this point again. This is also theta equals 2 pi. So we're right back to where we started. And then with our understanding of the periodicity of trig functions, we see that we're just going to keep retracing the same exact curve over and over and over again. So this entire curve is sketched out when theta ranges from 0 to 2 pi. All right, so now that we have these 4 points, we have to sort of know how to connect them. And we could, if we wanted, we could find more values, like between 0 and pi over 2. We could compute the r values for pi over 3, pi over 4, pi over 6, and that would give us some intermediate points. But if we just want a rough sketch of what this looks like, then we can use the fact that polar coordinates typically describe curves that are circular in nature. And so in this case, this curve is going to look something like this. We have sort of a half circle looking shape that goes from the first point to the second point, from theta equals 0 to theta pi over 2. It's going to continue nice and smooth until this point here. Kind of another, maybe an oval or ellipsoidal curve looking thing there. And it's just going to continue this way all the way around. And at the point where theta is 0 and pi over 2, we do have kind of a little point there that it comes together. So this graph is going to look something like this. And for, I think obvious reasons, when you look at the picture, this is called a cardioid. Right? And so a cardioid is a collection of graphs that are very popular in polar coordinates. They come about in all sorts of contexts with polar coordinates. They're easily described as you see here, r equals 1 minus cosine theta. And typically when you have a cardioid, you know it's a cardioid. You just have to figure out where the top of that heart-shaped part is, which direction is the cardioid oriented. In this case, the top of the heart is pointing in the positive x direction. Of course, you can have it pointing up, down, to the left, diagonally, wherever you want. There's all sorts of variations of this. But being able to understand that the cardioids look something like this, once we know what this one looks like, we can graph other ones similarly in a similar fashion.